Okay, yeah, I'm from the University of Cologne, where I'm doing my PhD, and I'm sure you all know these situations where someone asks you, tell me the title of your PhD project, and then I'm like, well, it's the backside of graphene manipulation by intercalation, and then it's fun to watch people's faces go blank, and when they recover, they're like, okay, what the hell? Or, as they say in Cologne, was soll der Quatsch? And then in the following, I want to convey basically the basic idea of my PhD project. So I'm a surface scientist, and surface scientists study surfaces, and just to make sure we're all on the same page, what's a surface? This is a solid, and right here, that's where we have the surface, and this is quite hard, and we don't care about all of this nonsense, yeah, as a surface scientist. And the surface that I'm studying is called graphene, and graphene consists of carbon atoms arranged in a hexagonal honeycomb lattice, like you can see here, and the nice thing, and it's a two-dimensional material, that's the nice thing about it. So it's just one atomic layer thick, so that's the top view, and if you look at it from the side, it just looks like this. And there you immediately see why graphene is such a nice thing for surface scientists, because it has two surfaces and nothing in between. It has some other nice things, so it has electronic properties, quantum mechanical phenomena, it's extremely strong and almost transparent, and on the Nobel Prize poster, for example, this is summarized by this cat, that's Schrödinger's cat, standing for the quantum mechanical stuff. And if you have a graphene sheet, you can actually carry around this cat with it, and it helps that it's Schrödinger's cat, so in 50% of the time it's dead and cannot tear up your graphene. But actually what I'm interested in is this two-surface kind of property. So what I want to do in my PhD thesis is I want to put something here on the back side of graphene and study how it influences with something that is sitting here. So on the front side, that's reactions or how it binds, stuff like that. What I want to do is kind of position the cat where I want it to. And the task, the idea is that we can position the cat by putting mice underneath, and then the cat will go where the mice are. And now, of course, the task is to find cats and mice on the atomic scale. Currently we're exploring like a bunch of possibilities how to do that, and today I want to just show you like a working example. So the simplest idea is, because we grow graphene on a substrate anyway, we just use the substrate as mice, and the substrate is iridium, and as a cat we will put platinum on top. So let's have a look with scanning tunneling microscopy, that's my method, how graphene on iridium looks like. This is a high quality layer of graphene growing over like a stepped iridium surface, and you see some dots. Those are not the atoms, but they come from a moire superstructure. You get a moire if you put two lattices on top of each other that are like slightly different in size. So in our case, graphene on iridium, and there are the dots. And now we take the system and put platinum on top, and this looks really surprising because you would think that maybe the platinum would just form like a film, but what it actually does, it gives a regular array of clusters, and each of these clusters, and they follow also this moire periodicity, and each of these clusters contains about 70 platinum atoms. Now this looks really nice, but we found that getting funded for making nice pictures is quite hard, so we decided against that and said, okay, we just want to understand the binding mechanism. What's the binding mechanism? So basically, in order for platinum atoms in order for them to bind to the graphene, the carbon atoms have to rehybridize. So from sp2 to sp3, that gives you an extra bond, and then a carbon atom binds alternately up to the platinum and down to the iridium. And it's 2 points that are important here. You need the downward bond in order to get the upward bond. And the downward bond only works if you have an iridium atom directly below the carbon atom. Otherwise, the whole thing doesn't work. And this is the case, that they're directly on top of each other periodically, because the lattices don't match all the time, or they don't match. And now, of course, we got the mice and cat, and now we said, when we understood the binding mechanism, can we prevent this cluster formation? Yes, we can. We just put oxygen underneath or beneath the graphene and above the substrate, and that kind of blocks the substrate. And the way this works is, so it was named the Captain-Jack-Sparrow effect, that came from my supervisor. And the oxygen sort of dives underneath the graphene that you can picture as anchored to the iridium, cuts those lower bonds, and then the upper bonds are not possible anymore. And at the end, I want to just show you like a live demonstration of, now I clicked one, live demonstration of the Captain-Jack-Sparrow effect. So you see a regular cluster lattice, and then we turn on the oxygen. You see that they start moving because they cannot bind anymore. Where do I press? Ah, okay. So there you see that they start leaving their regular lattice. Okay, that's it. Thank you very much.